Hello and welcome everybody. My name is Noman. I am a senior manager at Synopsys, and this is my talk about basics of wireline transmitter circuits. So you already been through one of the great professors and in their talks. I may not able to match with their talks there, but I will try. I'll try my best. So I did my PhD from University of Waterloo in Canada in 2011. I worked in different analog design roles at Philips and Maycom. Maycom is from Massachusetts as well. Movalis, and right now I'm a senior manager at Synopsys and leading a 224 gigabits per second SerDes development. And I don't have too many areas of expertise. I just know wireline circuits, so like that. Okay, so before we go into the detail, I want to start with the motivation for the wireline circuits. So as you can see, that with that over time, the amount of data being generated is a staggering amount. So you can see that in like 2025, we will be almost generating like 200 terabytes of data. So, sorry, zettabytes of data, I'm sorry. Zettabytes of data. And what is one zettabyte? One zettabyte is 1 billion terabytes. So put it in perspective there. So what does that mean? So assuming we have a hard disk, nowadays external hard drive is like 1 terabyte. You need 200 billion of those terabyte hard disks to store the data only for the year of 2025. I'm not saying the data about later years, only for 1 year of data. So now you got that information. The other information is from where this data is being generated. And the second part of the graph will tell you a little bit more about this thing. You may have already seen most of these things in your social media account. For example, you can see that within 1 minute of data, this is data generated by Domo, that within 1 minute, how much information has been created using our cell phones and using our social medias or our laptops. You can see that Twitter, how many tweeting, 360, I cannot even read from here, 360K tweets were done, WhatsApp messages, we have LinkedIn, DoorDash. You can see quite of these things, 241 million emails going through Facebook account, ChatGPT, Instagram. These are, you're already aware of most of these social media and social media accounts there. So this is how we are generating the data. So now you can making a little bit of more sense. The next part comes in that where this data is being going through. So first information is that when we go through Zoom meetings or through using WhatsApp or other things, this is a very small part of the total data communication happening. Is, as you can see from Cisco's 2021 index page there, that only 15% of the data is being used during the data transfer between humans to the data center. For example, when I send a message, WhatsApp message, it goes through a data center and then goes to another. That's total amount is less than 15%. And then the other 14% goes between data center to data center. What does it mean as well? So we have to think from that perspective, that assuming you uploaded a YouTube video, you want somebody from other side of the world wants to see the same video as well. So you need to replicate the data. Same data, you need to go to another data center. That is only 14%. The most amount of data, more than 70% data has been used within a data center. What does it mean within a data center? That once, for example, I'm giving an example as a YouTube video. When you upload a YouTube video, it needs to go through a storage, first of all, then it needs to go through a tagging, it needs to go through its encryption, it needs to find out some other information from that YouTube video. This all information, or for example, tagging the data, machine learning, all this information stays within the data center. And that data center consumes about, like that data center movement is about 71%, 72%. And for those data center, we need a very high-speed communication system. I call it like a wireline circuits, but we need a very fast or federal links. It could be optical links, it could be electrical links, but they need to be very, very fast. And when we're talking about data center, there are many things you talk about a data center, like a cooling part or the how much energy consumed. But most of the things which we are concerned about when we are talking about the data is TPA and L, which is a power, performance, area, and latency. What does it mean is that we need to make sure the power is as low as possible. So otherwise, we need to cool down our data center. We need to have a highest performance. As you already know, we want to have a lower area because bigger chip takes more area. And latency. Latency means how long it takes from data to go from a data center all the way to our cell phones. For example, you have seen like YouTube is doing or Netflix even doing like live boxing match. There was few months back happened. So if you have a big latency, you cannot even watch all these things. So these are important parameters. I'm going to give you a philosophical overview of SerDes. I call SerDes, I have not even explained that concept here, but you can think about SerDes as like a wireline communication. Think about it that people are going I'm from Toronto. I'm going from Toronto to Sydney. My brother lives in Sydney. So I'm just giving an example. It looks good on a map as well. This one way, there are 200 people going through it. And one way is that everybody has a jet and they all go through a runway, and we have 200 of captains and 200 of crew, and we all go crossing the airspace, reach to the destination. It does not seem feasible. It does not make sense to us. What does make sense to us? That we bring everybody to the airport, pack them together, and send through an aeroplane all the way to the other side of the world. So you can think an aeroplane as a transmitter, which I'm going to talk about it more in an electrical sense, but that aeroplane has to travel through the airspace and has to able to deal with the turbulence and all the other things while keeping the power and performance intact as well. That's what we want to do. So that's the thing, that rather than having a parallel one, it's better to have one serial communication. I was giving an analogy as an aeroplane. I'm going to keep this analogy in place when I'm going through my more technical aspects. I want to keep a little bit high level there. But you can see there's one important issue, that we are adding a latency. What is latency? You're adding more time to reach to one place to another. For example, for me to come from Toronto to here takes me 1.5 hours in aeroplane, but it took me 3 hours before that to be at the airport, to go through the check-in, through the security, through the immigration. And that adds up to the latency time. So when we are doing the serial communication, it makes things easier, but it adds time, unnatural time to the. That's why all the big millionaires have the jets, because they don't want to waste time on that latency as well. Okay, I'm going to keep that analogy. I want you to keep that analogy in place as well when I'm talking more into transmitter part. So as I mentioned, that parallel communication is not very suitable because it adds crosstalk, clock skew. Crosstalk, you can say, from the air issues there, and then we have a high pin counts in a pin. So what we do is that rather than sending the data in parallel, we can use the transmitter, which is on the left-hand side, and it sends the data sequentially through the channel, and it goes through the channel. This is my channel. It goes through the channel and goes to the receiver. So in terms of analogy, rather than having all the data going directly, we go through a channel, go one at a time, reaches to the receiver, and at receiver we can take that parallel data and make it work for us. And this solution, we call it SerDes in short form, or serializer and deserializer. We're serializing at the transmitter side and we're deserializing at the receiver side. And we use it as a time division multiplexing. So we're using time to multiplex the data. Now I'm going into a little bit of circuits here. So this is a block diagram of a SerDes, which we use quite often in our design. This is up to 56 gigabits per second. I'm just saying these are a little bit older information. Nowadays the things have changed, but the basics remain the same as well. So I am talking about the left-hand side. The box on the red dotted line is called transmitter, and on the right-hand side is our receiver. and the receiver will be on the next talk. One of our colleagues who's going to talk about it on the receiver. I'm going to stick within the transmitter side on the left hand. And transmitter is actually, you can think about it, that we take the discrete data and convert it and send it through a channel and convert it into analog data. Discrete data comes from GPU, CPU, any other data which is coming parallel to us. It comes to us and we mux them. Mux is a fancy word. I don't know if you heard it or not, but you can say we do a selection. We select the data and we select one data at a time, and we send that data through FFE. FFE is also another jargon I used. It's called feed forward equalization. I will talk more about it. And then we drive it through the channel. And you can say driver as an aeroplane in terms of analogy there. And it sends the data through the channel. And what does it mean by channel? And we can say the channel is the transmission media for the analog signal. And that channel could be anything. There could be a wireless channel as well. But in this specific context, we are talking about electrical or copper interconnects. So I'm going to stick to that one. Otherwise, the channel could be anything. So just to give an example, what do you mean by channel? So I'm giving a small, try to give an application space. How does the channel looks like? Assuming we have a PCB, the green one is a PCB, and we have two chips. Okay, please bear with me. I'm using some jargon as well. Assuming there are two chips there, but these chips can have different dies inside there. So we can assume that there's one die which is connected to another die, and they are on the same chip. So what happens is that you don't need that much of communication. They will be very, very close to each other, maybe like in millimeters of distance. So we call them XSR, like extra short range channel. And the same concept, we keep going up. For example, if this chip wants to connect through the optical to the output, it goes through a PCB trace, and we call them, PCB might be 6 or 8 inches long. So it may go through the PCB, it may call it a VSR channel. We can use a twin Rex cable to connect from one part of the chip to another chip. We can also use optical fiber and so on and so forth. So you can see the channels, they're different amount of channels, and for different channels, we need to change the characteristics of our transmitter, we need to change the characteristics of our receiver, and so on and so forth. So I just use few words. You may hear a lot about them. It's called XSR, the extra short reach. VSR, usually connected with the optical. When we connect with the optical ones, they use VSR channels. Medium range is between, usually between one PCB to another one, whereas the long range is from one PCB all the way to maybe other part of the data centers too. So now I'm going into the more details of what the transmitter is supposed to do. Transmitter, as I said, keep an analogy with in terms of the aeroplane as well. So what transmitter has to do, as I said, the main job is to serialize the parallel data. The parallel data is coming in, it needs to serialize it. What it needs to do, it needs to do it at the full rate, because there are different rates for different application. You want to make sure it is working at that speed. We need to maintain the precise timing as well, because the receiver will not know when the data is coming. So it needs to be precisely send the data exactly at the allocated time. We need to know what is the modulation techniques. Modulation techniques means that once the data is received, it needs to know is the data is 1-bit information or is it 2-bit information, or it has different bits of information. We call it a modulation. It needs to provide sufficient voltage swing. Of course, that the bigger the swing, the better it is to figure it out. Provides appropriate equalization. I use the word equalization here. You can think about that when aeroplane is going through airspace and the air pocket comes in or the storm comes in, it needs to be able to recover from all these imperfections, or the headwind, tailwind. All these things, it needs to be equalized to make it through it. So that's part of equalization we use. And above all, it needs to be done with a low power and as less area as possible. Now, when we're dealing with the transmitter and when we send the data through a transmitter through a channel, the channel has a low pass characteristics. So what it does with the channel 1 and 0s we are thinking we are sending 1s and 0s. But technically, when it goes through the channel, it gets some kind of an imperfections in it. We call it ISI, or a low pass characteristics. And that low pass characteristics, you can see that our waveforms are not ones and zeros. They are look like somehow analog signals. In order to see the whole waveform, it's not very easy for us to look at the whole waveform. So what we did is we came up with a very important concept in wireline transmission. It's an eye diagram. Eye diagram tells us a lot about how our transmitter is working through a channel. And you can see what does the eye diagram look like. I try to make this animation, make it more interesting, but let's see if it's interesting enough or no. But what it does is it takes a small chunk of data in a small amount of time and start putting on top of each other. So rather than seeing the whole waveform, we see a snapshot of everything on top of each other. So now if we see some kind of imperfections in our transmitter or through the channel, we can look through the eye diagrams and analyze our circuit. So eye diagram is a very important diagnostic tool for us to understand the concept or the feasibility of that specific transmitter. So let's go to the next step on the eye diagram. So I'm going to talk more about it, eye diagram. So this is the NRZ eye diagram, non-return to zero. There are different eye diagrams. We're going to talk about it. But these eye diagrams will tell us more about how the real eye diagrams will look like. You can see we give some kind of a horizontal, we call it horizontal eye opening. This is the eye width as well. And then we have a vertical eye opening. This is eye width in this case there. So what happens is that we want our eyes to be big enough. The reason we want to have a big enough is that the receiver, you can assume the receiver is simple comparator. And if I have a comparator which has a zero crossing, so if it compares the data and the data is higher than zero in terms of analog, it knows that the one is sent. And if it is below zero, then it's highly likely, I'm not saying exactly, highly likely it is sending zero. So this eye diagram is a very important tool in our understanding of the circuits. So why we use eye diagrams? So at the end of the day, I don't care about the eye diagrams. What I do care that when I send the data from one side, it reaches to the other side. You can think from the analogy of the airplane. I do not care how the airplane flies. I do care that my family, if it's leaving from Toronto, they should safely reach to the other side of the world. That I do care about it. So the problem is that in terms of in wireline communication, we usually design say in terms of BER. We cannot say that the link is error free. We say the link has a bit error ratio or bit error rate. What does it mean? That, for example, 10 raised to the power minus 12 bit error rate means that if we send 1 trillion bits, we may get one error. Simulating that 1 trillion bits in our recent, whatever GPUs or CPUs we have, is a non-trivial task. It will take years, if not months, and we may be old by that time to get this thing BER done. So that's why it's not very easy to run the BER at the circuit level. What we do is that we look at the eye diagrams on the left-hand side and we try to extrapolate that how the BER will look like eventually by looking at our eye diagram. And you can see I put quite many numbers here. I don't want to go too much into detail in this one. But we can say that when we look at this total jitter, which is the zero crossing, we can say that the zero crossing has a deterministic jitter and some kind of a random jitter associated with that one. And that random jitter is dependent on how much BER we want to tolerate for that specific channel. Okay. So this is a design decision matrix. So when we are designing a TX, usually we look into these things, not exactly in a same order, but we look at few of these decisions. I'm just going through in a clockwise fashion. We talk about the modulation. We talk about what is the final mux. These things may look like a jargon to you, but we will eventually touch base with them slowly. The other one is what is the output driver will look like. The fourth option is that, do we still stick with analog based transmitter, or should we go more into digital based transmitter? And then there's a one called UI pulse generator circuits and the pad natural network, which is much more advanced topics here. So before we go into this one, let's go talk about this modulation technique. So the most common technique is called NRZ, or the non-return to zero. In NRZ modulation scheme, we send only one bit of data. Either it is one, or in this case, I call it +1 and -1. So when you receive the data, the receiver will know is the information is given 1 or 0. But we realize that it is a very waste of information, waste of time. So why not we send more data in the same amount of time? So we came up with different modulation schemes. PAM3, PAM4 has become a much more bigger standard. In what we do is that we send 2 bits of information in the same amount of time. So now technically we increase the data rate by twice without doing anything bad to our transmitter and other thing. The only problem is now the receiver has to work with much smaller SNR, or the signal to noise ratio, because now before the signal to noise ratio penalty was 0 dB. Now for PAM4 it's about 10 dB because the I width is small, I height is small. So the design complexity increases, but we learn to deal with that one in receiver. So PAM4 is becoming a much more of a standards going in an optical and in electrical as well. And we are also talking about PAM6, PAM8 going forward too. So now go to another part of the transmitter. It's called like a serializer. It's a little bit of a busy slide, but it may not look very intimidating if you start thinking what we are doing. They are flip-flops, assuming you know flip-flops what it is. So these flip-flops and the mux, which is the selection, a fancy way to say that we are selecting the bits, the 2 bits coming in, we select one of them. They're different kind of a muxing involved into this one. So serializer is just a cascade of muxes. You can think from that perspective as well. For example, the 4 bits of information coming in, we can mux them into 2 bits, and then two bits are muxed or selected 1 bit at a time, and it will be flopped on the final flip-flop through the driver to the output. And we usually call this full rate mux. We realized very quickly, this is done like many years ago, like maybe 15, 16 years ago, 20 years ago, these ones we used to do full rate. We moved to half rate mux very quickly. We find out that for less than 50 gigabits per second, we don't need the final mux, and we can only use like half rate clock. So now the clock is better and it's less power. So we can technically ignore the final flip-flop. The same concept of half rate can be extended to a quarter rate. I did not go through the total too much into technical details, but you can think that rather than having like a half rate, we can have a quarter rate. And this quarter rate has become a much more mainstream nowadays with more than 100 gigabits per second data rate. But 4-to-1 mux, as I said, is become more mainstream. The only drawback is that to mux 4-to-1 or the final mux, you need 4 of the phases there. And I call those phases as like the phase 0, 90, 180, 270. And they need to be combined in a fashion using some kind of a logic such that we can able to select one of the data. This is the waveform. If I have time, I can go back into this thing end of the talk. So this is the mux architecture here. So the final mux, we can, as we said, this like final mux is a 2-to-1 mux and the driver. Professor Ali already mentioned about Thevenin and Norton equivalent circuit. Exactly the same concept applies here. We can send the data using a Thevenin equivalent circuit, or we call it like a voltage mode logic, or through a Norton, we call it like a current mode logic. Well, let's go to the current mode logic. So this is the first circuit I'm showing, but you can see the circuit is very basic. What we are just doing is that assuming we have information is coming, that data on the P side is 1 and the data on N side is 0. What will happen is that since this transistor is on, or this NMOS is on, So the current will flow from this RT, or the termination resistance, go down, and one of the current will flow from the other RT, goes to this one. But this path has 3 RT in their path here. So that one-fourth of the current will flow through this path, 3/4 of the current through this path, because this current is kind of a constant I bias. And when we do that thing, this 2 RT, or the termination resistance at the receiver, will generate will have a voltage output, which we can plot it here as a two-level signal. So if the signal is 0, it will be on that side. When the signal is high, you will look at the output, and it will look like an NRZ I diagram. And the signal swing depends on the bias current and the termination resistance. The same concept we can go to the PAM4. So in PAM4, we already mentioned there are 2 bits of information we are sending. So we have an MSB and we have an LSB. So we can combine these 2 bits into 2⁻², 4 bit of information, and we will get a PAM4 eyes like that. Now, we talked about the current mode logic. Now we're moving into the voltage mode logic. So what we can do is that we can use a simple inverter to send the data through a channel. And in this case, I'm showing it. You can terminate at the receiver. You need to think about it, why we need to terminate it. Okay, if you don't know, you can ask the question. I can answer it. But we terminate the data at the receiver. We can terminate it single-handedly, and we can terminate it differentially. But you can see it's a very simple inverter, and go back to the initial talk from Bill that everything is an inverter. It looks like an inverter at the end of the day. So now, this is not a practical version. The practical version is called source terminated SST driver. And SST driver is exactly the same driver, like a simple inverter. But the problem with this inverter is, as Nigar mentioned, and also the same thing Professor Ali also, Sheikh Oslami also mentioned as well, the resistance of that NMOS is not highly controlled. It can move around for different reasons. So to do this, we cannot use that resistance of the NMOS as a termination resistance. So we need to add a passive termination resistance, in this case, RT in series, so that the RT plus RZN, I call it the impedance of that NMOS, should be equal to 50 ohms. And this is how the SST driver will look like. And the signal swing does not depend on the current. It depends on the voltage or the supply voltage, VDD by 2. Same concept. We can do it for the SST driver for the PAM4. You can see the PAM4 will have 2 different kind of levels. Either the inputs are the same or they are different. And if you put them together, we will get different voltages. And for a VDD of 1.2 case, you can see we can get a very nice 4 levels of PAM4. Before we go into the other step, there's a called FFE. FFE is called feed-forward equalization. As I said, that we need to equalize the channel. We know the channel is coming in. We need to somehow equalize it. And one of the ways to equalize the channel is to use an FIR filter, and which it does is that it delays the data. We call it a TB. In this case, is the time you delay by that same amount of clock. But you combine those data with some kind of a weighted sum, so that now you pre-distort the signal. And what does it do is that if I look at this figure, start with on the bottom, we have a red dashed line. This is the input. If I don't do anything, I send this data, and the output, it's coming out as this unequalized I diagram. And you can see the I diagram looks pretty bad. The reason is the receiver does not know. When it samples the data, it doesn't know that data is 1 or 0. So now you will lose bits. So what we do is in FFE is that we pre-distort the data. We already know how the channel is going to respond. So we pre-distort the channel, and that pre-distortion you can see in a blue solid line in the input. And when we send that data through the channel, you can see the output will look like on the right-hand side, this red one. This is an equalized eye. Now you can see the eye is open. So the receiver has much easier time to detect whether it is 1 and 0. but at the same time, you can see that the output swing is reduced. It has its own imperfections coming into the place there. And these are done using the weighted sum. We talked about the weights before. And these weights are usually used using a different optimization schemes. And one of the most common optimization scheme is called minimum mean squared error. So we take the error, what is coming in, and it is being used in machine learnings and all these optimization algorithms too. So this is my second last slide, something like this. So what we are talking about is that this analog TX, we have been using it for a long time, for up to 50 gigabits per second. But we realized very quickly when we go in higher data rates that we need to do things in digital domain much more efficiently. For example, FFE we can do efficiently. We can do modulation efficiently in the DSP. So we are going towards more DSP-based transmitters. And what it does is that all the equalization and modulation is usually done in the DSP, and the serializer will stays as is, and the DAC is, we call it a DAC-based design. Rather than a driver, we're calling it a TX DAC. And in the recent studies, we have found out that more than 65% of the research of the papers are DAC-based or DSP-based TX. This is my last slide, second last, put like that. So this culminates the whole design. If I design the most industry standard, the fastest SerDes, this will exactly look like that. It looks overwhelming, but you can see that the DSP is doing the PRBS generation, FFE calibration. That's the one we already talked about it. We said what is a serializer? If I remind you, serializer is a bunch of cascade of muxes. So it is doing the same thing, and then muxing needs some kind of a retiming of data, which comes from a digital background. So you retime the data, you mux it, you do some kind of a processing on what kind of a bits or DAC bits you need. This is done in the data path, and that final information goes to our 4-to-1 mux, which we also talked about it. And that 4-to-1 mux goes to the driver through the different DACs, we call it, because I showed in this fashion, through the output to the pads. And to do this, usually sometimes we use a dual T-coil to optimize, because pad has huge capacitance, ESD has huge capacitance as well. We need this kind of a dual T-coils to improve the return loss or the signal integrity part of that circuit there. And as I mentioned as well before as well, that we also, for 4-to-1 mux, we need 4 phases of the clock. And to do this, we sometimes use ILOs, we use DLLs, this delay lock loop, we use some kind of a PLL as well to generate these kind of a different phases, because we need 4 phases of the clock. And of course, we need a phase rotator to move the phases such that the data, the handshaking the data between the serializer to the DAC can be done effectively, efficiently there. So this is a summary of my slides again. So I talked about 4 or 5 topics, but there are 2 advanced topics about a pulse UI generation and the pad matching network. And these are the very active area of research. So if you go, I would encourage everybody to go into grad studies. And when you go into that grad studies, go into transmitters as well. And you will see that the pulse, 1I UI pulse generator circuits are one of the most important blocks. They are the most important building blocks to make things better for the next generation of transmitters. If you want to do research, this is one of the best areas of research in transmitter, not only in the copper interconnects, but also in the optical interconnects as well. These are the few references. So one other thing is that I did a 3-hour tutorial on the similar thing. This is a condensed version, half-an-hour condensed version. That other one is a 3 hours lecture. So you will go much more into detail into each individual blocks if you are interested into this one. And also you can read the article as well. So this is, and I'm also presenting on CICC a 224 gigabits per second. This is the industry fastest speed SerDes by far. And we are the first ones who did it as synopsis as an IP at least 3-4 years ago. And we presented it last year in ICC, and we are presenting it, updated results in CICC in 2 days as well. Okay, thank you so much. I think I'm exactly on time.